again. So we'll start now on chapter 18, which is probability distributions. It just takes this, the first part of this just takes us a little bit further than what we've already done, and then we get into some more complicated stuff later on in chapter 18. So to start with, a probability distribution is really just showing the possible values that we could get from rolling a dice or from any event. For example, if I roll a dice, then there are 6 possible outcomes, and if it's a fair dice, an even dice, then the probability of each one is 1/6. So we could put so x is what we call a random variable. When you roll a dice, the outcome could be 1, 2, 3, 4, 5 or 6. So the probability that the value of this is equal to 1, 2 is 1/6, 1/6, 1/6, 1/6, 1/6 and 1/6. Nothing too exciting yet. Maybe we could have an unfair dice. And in the casinos, sometimes people will take their own dice in there and try and swap them over. I don't know if that happens anymore, but maybe it was just in the old movies in the saloons. But where they would shave the dice, and so instead of being a perfect cube like that, it might have been not quite cube, so that instead of those 3 sides being equal, one was not. And so if it had a slightly bigger face, more likely to land on that. Only a little bit, but you don't need much of the odds in your favour to make a lot of money. I've tried, not shaving dice, but often doesn't work. So maybe you would have something like, with an unfair dice, x, probability that x equals x. I won't do it as fractions, I'll do them as decimals. So again, x will be 1, 2, 3, 4, 5 or 6. And so perhaps you've made it so that 6 is more likely. So instead of each of them having 1/6 or 0.166, 0.17, let's say 0.20, 0.20, and then 0.15, 0.15, 0.15 and 0.15, something like that. I guess if we know about dice, then the opposite sides always add to 7, so if 6 is very likely, then I guess 1 would also be equally likely. It doesn't matter. What we've got here is that the sum of those probabilities is 1. Hopefully the sum of these is also 1. So, that's the key point. The sum of the probabilities, okay, let's spell probabilities as I can. Probabilities must be 1. The sum of the probabilities, alright, a little confusing middle of that. And so what often happens is that they'll put in an unknown. So for example, we could have, x, and the probability that x is equal to this value, 1, 2, 3, 4, 5, and 6. It doesn't have to be a dice, it could be anything. This one's got 6 different possibilities. So it might be k, 2k, 3k, right, so that k, 2k, 3k, 0.2, 0.3, 0.2. I've tried to make this up so that we get reasonable numbers for it. Well, I know that those must add up to 1. So k plus 2k plus 3k plus 0.2 plus 0.3 plus 0.2 has to equal 1. That's 0.7, so that's 6k plus 0.7 equals 1.0. So 6k equals 0.3, so k equals 0.05. So this then becomes 0.05, 0.10, 0.15. And if we've done it correctly, should add up to 1 again, at 0.15, 0.3, 0.5, 0.8, 1.0. Alright? And so we can answer questions on this. Probability, x is greater than 4. Probability x is not equal to 2. Probability of two throws, both greater than 3. Alright. So probably a good thing to do now would be to pause your video, have a go at those 3 questions, and then come back to it. Alright. I'm not going to pause this because then I've got to save it as 2 different files and so on. Welcome back. Alright. Probability that x is greater than 4. It doesn't include 4. Greater than 4 is this, is 0.3 plus 0.2 equals 0.5. You don't have to show that step, of course, just to make it there. Probability of x not equal to 2. Probability of x is equal to is 0.1. I can add up the others, or I can just say 1 minus that. 1 minus 0.10 equals 0.9, 0.90. I think it's 0.5 exactly, it's 0.9 exactly, and so that doesn't need to lead to 3 significant figures, but that's so that's fine. Probability 2 throws both greater than 3. Greater than 3 means this bit here is 0.7. The assumption here is that the throws are independent of each other, so if I throw a 4 on the first dice, it doesn't mean that that's less likely or more likely to happen the next time. So it just becomes 0.7 times 0.7 equals 0.49. So I've got nearly a 50-50 chance of getting a number greater than 3 both times. Okay. The mode. The mode, we've used that before in stats. You probably did that in year 7, 8, 9 maths, where you had a whole set of data and you worked out the mode. The mode is the most common or the most likely. In this case, we'll go 5.1, 0.15, 0.2, 0.3, so the mode is 5. So that's the outcome, which is most likely. So the mode is 0.3. So we need to be careful. Okay, what's this table telling us? When we roll the dice, the probability we get a 5 is 0.3. The probability we get a 6 is 0.2. Sometimes more than one mode. So for example, instead of 0.2, 0.3, 0.2, I might have had 0.1, 0.3, 0.3, in which case 5 and 6 were equally likely. I'll draw that up. So x is 1, 2, 3, 4, 5 and 6. We use the same k. I'll put the numbers in this one so we don't have to work it out. 0.05, 0.10, 0.15, 0.2, 0.1, 0.3, 0.3. In this case, 2 modes. 5 and 6. This is a bimodal distribution. The one above has got 1, mode, so we call that unimodal. Unimodal 1, don't necessarily need the hyphen in there. I'm not sure if they use a hyphen or not. Unimodal or bimodal. No, they haven't got any hyphen in there. Either way is fine. Okay. Alright. So we'll keep going here. So that's sort of 18A covered. 18B just takes us one step further. The expectation or the expected value it's the overall or average outcome. So with what we had here, you know, if we had a normal dice, a fair dice, then each of these, 1, 2, 3, 4, 5 and 6 would be equally likely, and over a lot of throws, the average number we would get would be, as multiplied by 6, it would be 3.5, be right in the middle of it, wouldn't it? All right, and so that's the expected value. So what are we expecting in the long term? And that then becomes quite important when we're looking at games of skill and chance, betting on the horses, touch lotto, lots of different things like that. Of course people are trying to increase their chances of winning and to know what the expected outcome is. Now it's not always going to be as neat as everything equally likely. But the expected value or the expectation, I tend to use expected value, but I think they're using expectation all the time there. Expectation, we write that as capital E of X. The expected value of X, or the expectation of X, is the overall long-term average for a normal dice. So in the middle of 1 and 6 will be here. But we need a better way to calculate it than just looking at that and saying, oh, they're all even, because in most cases they're not going to be even. It's the sum of, so this means the sum, that's sigma, which means the sum, sigma is the Greek letter S. You're probably familiar with the Greek letter sigma like that. That's small sigma, that's capital sigma. So the sum of X times the probability of X equals X. So again, for a normal dice, it becomes expected value of X equals 1 times a sixth, so the sum of it, altogether, plus 2 times 1/6 plus 3, times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. I haven't got the table there anymore, but 1, 2, 3, 4, 5, 6, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. So the sum of x times the probability that x equals x. 1 times a 6 plus 2 times a 6, 1 times a 6, 2 times a 6, 3 times a 6, add them up all up. So it gives us 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6 equals, hope this works out, 3 and 3 are 6, 10, 15, 21/6 equals 3.5 and 3.5, as we expected, you know. So we expected the expected value and the expectation. Let's leave this one. So for our loaded dice, the expected value of x, just looking at the table, and again, it's all very well to do these calculations, but you know, I mean, there was every chance I was going to make a mistake on this here, you know, and muck something up. But I knew where I was going. If I didn't get 3.5 there, I was going to go back and check it. I don't know what the value is going to be here, but 0.05, 0.1, 0.15, low probabilities and higher up this end. So the expected value is pushed up this way. If they were fair, it would be 3.5. It's going to be more than that. I don't think it's going to be as much as 5, but you know, I'm expecting, you know, 4 and a bit. So it equals the sum of x times the probability that x equals x. So it becomes 1 times 0.05, 1 times 0.05 plus 2 times 0.10 plus 3 times 0.15 plus 4 times 0.2 plus 5 times 0.3 plus 6 times 0.2. Okay, that gives us 0.05 plus 0.20 plus 0.45 plus 0.8 plus 1.5 plus 1.2. 1.2. So that bit there is added a fair bit to the expected value. There's 1.5 just from that. So we get 45 and 5, that's 0.5, 0.7, 1.5, 1.4 is 3, 4.2. That seems reasonable, you know. I thought, you know, my guess was not going to be as high as 5, it's going to be 4 point something. I didn't guess any further than that, but, you know, had I forgotten something, left something out, and ended up with an answer less than 3.5, well, if I got 3.6 or 3.7, I said, gee, I thought it would have dragged it up more than that, because I know it's 3.5 if it was all even. But, you know, 3.6, 3.7, so gee, this hadn't had much impact. But 4.2, that seems reasonable. Had I got 3.1, that can't be right. What have I done wrong? And check back through what I've done. Okay. Yeah, a couple of tricky ones there in the questions for 18B. Let's have a go at one of those together. So, 18B question 2. Question 2. Random variable x has probability that x equals k times x plus 1. The probability that x equals k times x plus 1. So this equals k times x plus 1. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay. So this one becomes 3k. K times 2 plus 1. K times 2 is 3k. Here's 4k, 5k, 6k, and 7k. K times x plus 1. K times 6 plus 1. K times 7. So there's our probability distribution. The bigger numbers are more likely. It's clearly not a 6-sided dice. There are 5 bits on it. Whatever that is, doesn't matter. All right. First question then. Show that k is equal to 0.04. All right. Well, the key thing with any probability distribution is that the sum of the probabilities is 1. Sum of the probabilities equals 1. And I'll just use that as a shorthand. Sum of probabilities is 1. So 3k plus 4k plus 5k plus 6k plus 7k has to equal 1. 7, 12, 18, 25k equals 1, k equals 1 on 25 equals 0.04. Good. That's what they asked us to show. Find the expected value of x. Expected value of x. What are we expecting for the expected value? No pun intended. The expected value, what's the long-term value? Well, it's going to be somewhere in this region. It doesn't have to be one of those, it could be somewhere in between, like it was here, 3.5 and 4.2. If they were even, then the expected value would be 4, right in the middle. Equally likely 2 and 3 as 5 and 6. But 5 and 6 are more likely than 3 and 2. So the expected value will come up a bit. So not 4, but 4 point something. One will get the same as that there. Don't think so. I think, I'm guessing something like 4.5. 6 is far more likely than 3. 5 is quite a bit more likely than 3. So as a guess, I'm going to go 4.5. Alright, expected value is the sum of x times the probability that x equals x. So it becomes 2 times 3k. I could have said 3k is equal to 0.12. That would work. I can do it all at the end anyway. Plus 3 times 4k plus 4 times 5k plus 5 times 6k plus 6 times 7k equals 6k plus 12k plus 20k plus 30k plus 42k. 2 times 3, 3 times 4, 4 times 5, 5 times 6, 6 times 7. There's 6 and 12 and 20 and 30 and 42. Alright? That's 18, 38, 78, 80, 120k. We know what k is. We know 4. That gives us 4.8, I think. Okay, my guess was 4.5, but yeah, that's okay. I wasn't, my guess is not a calculation in my head to work out an answer. It's just, how do I got 4.2 for the answer? Okay, how do I got 4.8? Okay, it's somewhere, above that. But, it clearly can't be less than 2 and it can't be more than 6. The expected value is somewhere in that range, surely. And so, we need to, at least have a rough idea. Sometimes, students will get things around the wrong way and, end up with an expected value of 120. And that's not understanding what the question's about. Okay, let's stop at that. That's 18A and 18B covered. The binomial is 18C, and we'll do that next.